Hey everyone. All right, let's jump into it. Let's get it set up a little better first and change this light just a quick second. Okay, so we are going to talk about definite integrals using the substitution method. Previously, we went over u-substitution or the substitution method for indefinite integrals. This is where we said plus c at the end. So we'll talk a little bit about doing it with definite integrals today. And then we'll also talk about the area between curves, because up until this point, we've found the area under a curve and then above the x-axis. So now we're changing that to just say, well, what if we're under a curve, but then above another curve? So we'll go over that as well. So we're going to say definite integral substitution. Definite integral substitution, and the area between curves. Okay, let's switch out this marker really quick. All right, so let me give you a theorem for our substitution. We're going to start there, and then we'll get right into an example after this. So we have a theorem for this substitution that says the following. If g prime of x is continuous on the interval, and it's going to be from a to b, and f of x is continuous on the range of g, which I'm going to say is equal to u, then the following is true. Okay, so last time we talked a little bit about this idea of having like an inside function, and then that's when you're going to need to use substitution to evaluate the integral. So same kind of setup here, where g is going to go into f. So we have the integral, this time from a to b. This is the part that makes it definite instead of indefinite. And we have f of g of x. And then because of the chain rule, we have g prime of x dx. Okay, so just a quick reminder on this part, because the new part is what it's going to equal. We've seen this before. Remember, antiderivative is undoing the derivative. You're getting back to the original function. So this is just the case when your derivative had the chain rule, when you use the chain rule to find it. And so if you go backwards, the way we do that with integration is we do substitution. Okay, we went over this last time, but we're going to let part of this be u, which is the part that's like the inside part, and then account for what du is. We'll go through this today, so don't worry about it. And then the new part is our bounds. Last time we didn't have bounds, so we didn't have a and b. So this is the integral of f of u du. Okay, so we let u equal the inside part. We figure out what du is. And then the new part is we have to adjust the bounds, the limits of integration accordingly. So this is g of a and g of b. Okay, because originally this a number and this b number were in terms of x. But when we use substitution, they now have to adjust and be in terms of u. So you have to change your limits of integration. And so we'll just point to it and say the limits of integration have to change accordingly. They have to change accordingly when we use substitution. Substitution. All right, so let's jump right into an example of using this idea. So we have the following. We're going to evaluate the integral from -1 to 1 of 3x squared times the square root of x cubed plus 1 dx. Okay, so the first thing we're going to do is what we did previously, which is figure out the substitution so that we can eventually use like our power rule to integrate this. Now, if you need to, if it helps you, you can label that the limits of integration are in terms of x. So I'll do that in my work, but right now they are x equals -1 and x equals 1 because of this right here. This dx is letting you know that everything's in terms of x. So we're going to jump right into our substitution, and we're going to say, remember this process, we're going to let u equal something. And so when we let u equal something, that choice, I talked to you guys about this last time, that choice, the derivative of that choice needs to be present. And so if I look at my options, there's really only two things I could possibly do here. I could say u is 3x squared, or u is x cubed plus 1. And based on my choice, the derivative du should be there. And so I'm going to pick the inside of the radical. And normally that's how you pick also. You look at what's inside of something else. So if I pick x cubed plus 1, then that tells me that the derivative of u with respect to x is 3x squared dx. Okay, so that's why I pick my choice of inside the radical. It has the derivative already there. Real quick reminder, if this was off by a constant, it would still be okay. If this 3 was here, but let's say this 3 was not, or vice versa, that's okay. If it's off by a constant factor, you can still do this. And so we're going to substitute, but we're also going to need to change our limits of integration. So I'm going to substitute first, and I'm going to show you what I'm talking about. Right now, my limits of integration are still x. X equals -1, x equals 1. But now, this part here, so I have, I'm not going to rearrange it, I'm going to say it. The 3x squared and the dx are all getting replaced by du. So I'm just going to put that in the back. So we have square root of u and then du. Okay. If it helps, you can do an intermediate step where you put 3x squared next to dx if you'd rather see that, so you can call it du. Now, I have to change my limits accordingly. This is the new part. This is something we haven't done before because we didn't have limits of integration. So now I'm going to do all my side work. I'll go up here and say, let's go with red. When x is -1, my lower limit, okay, I now know that I need u, and I get that from my x value. So this is going to be -1. Let's keep this all red. -1 cubed plus 1, based on my choice for u. So if I simplify that, that's going to be 0. So my new lower limit for my integral is u equals 0. Okay. I use my choice for u to find the new lower limit in terms of u. We do the same thing for the upper limit. X is 1 was our upper limit. Plugging that into our choice for u equals 1 cubed plus 1, which is 2. Put that in red. Okay, so our upper limit is u equals 2. And then everything else was still what we already figured out. It's square root u du. And now this integral became much easier to do, and we're on our way to just use our power rule. Look at how it started, and now look where we're at. This is way easier to evaluate now because of our substitution. The new part was we had to adjust our limits of integration because we did substitution. So now I'm going to just say from 0 to 2, I know that everything's in terms of u. I'm going to write this as a rational exponent so I can use my power rule. So this is going to be u to the 3/2 over 3/2. And then with our definite integral, we evaluate it from our lower limit to our upper limit. Normally, you'll see like this line notation letting you know that you're going to still evaluate it from lower to upper. Now, according to your fundamental theorem of calculus, let me remind you really quick, your fundamental theorem of calculus says if you have a definite integral of f of x dx from a to b, then how you evaluate that is you find the antiderivative, you plug in the upper limit and the lower limit, and you subtract. Okay, so we figured this out, or talked about this before. And so now we're going to evaluate from 0 to 2. So we have, let's make this look a little bit better really quick. I'll do it in the next step. We're good. We'll just do it like this. So I have 2 as my upper limit, and then I plug that in to my antiderivative, and then I subtract, plugging in my lower limit. Okay, what I was going to do a second ago was simplify, but I'm going to just simplify now. Okay, so let's make this look a whole lot better. So this is square root of 2, you could say quantity cubed, and then the 3/2 that we're dividing by, you can flip and multiply and call that 2/3. And then this whole term is just 0. Okay, so remember rational exponents, the bottom number is the index, that's why it's a square root. The numerator is the power, and then the 2/3 came from flipping over the 3/2. And so our answer, if we just make this look a little bit better, that's going to be 2 square roots get squared, so that's going to be 2 times 2, and then another square root was left over 3. Okay, final answer. So this is how you use your substitution. If you have limits of integration, you have to adjust them accordingly. Now you do have an option to where you don't have to actually change it for you and for your limits if you remember to substitute back into or what you chose for u back. So let me show you what I'm talking about. So let's write it as a note. So I'll say note, you have an option. So you have the option to resubstitute. So resubstitute, and that's what we do with the indefinite integrals before evaluating. Okay, we'll say before evaluating the antiderivative. So we'll say, well, I'll just show you what I mean. Okay, so let me explain this part. So basically what I'm saying is you can actually decide not to do anything with this if you want. It's really up to you, and you can switch it up every time if you want. Sometimes you can find u for your limits, sometimes you can leave it in terms of x. It's really just what do you decide for that problem. So let's see if I can just squeeze that in maybe down here. So we had done all of our work, and we evaluated right here. So I'm going to kind of pick up where we left off. And let's say I never actually figured out that my new limits were 0 and 2. So from here, we don't need this anymore. We'll go right here. So from here, we could have said that we had u to the 3/2 over 3/2, evaluated from x was -1 to x was 1. And so what I would have to do there is just resubstitute the fact that u was x cubed plus 1. So 3/2 over 3/2. Move that a little bit out of the way. And that was x cubed plus 1. And I evaluate that from -1 to 1. Okay, and then you would end up getting the same answer. All right, so just so you're aware, you have options. And sometimes, like, you'll notice that it's a little hard maybe to find your new limits. Maybe if it involves like your trig identity or your trig functions, and it's not a precise number if you plug something in for like the angle of a trig function. But either way, you're going to get the same answer. So it's up to you. Okay, So that's how you're using your definite integrals and the substitution method. The next thing I actually want to talk to you about is involving symmetry, because of where we're headed next has to do with the area between functions. And so if you figure out that there's symmetry, then it's going to make your integration go faster. So let's get into that. Let's see. I think I left that up there last. So let's get rid of this part. Okay, so using symmetry. So using the symmetry of the graphs, pretty much, that you're working with. And so we have two options here. If your function is even, and a reminder from algebra, what that looks like. When a function is even, if you plugged in negative x, it's the same as if you had just plugged in regular x. That's the result for even functions. So if you know that you're working with an even function, and you can also tell from the graph, it has symmetry. So if your function is even, then if you happen to be integrating from negative of a number to positive of that same number, so from negative a to a of your function f of x dx, you can simplify your process a little easier and just say that your value is twice the integral from 0 to a of your function. I'm going to show you a visual for this so that it makes more sense. So for even functions, let's just draw a quick sketch. I'll just make one up. For an even function, it has symmetry about the y-axis. So I can say maybe like my function does something like this, and I'm finding the area below my curve and then above my x-axis. So what I'm saying for my integral here is maybe this is negative a and this is positive a. And so the way that that looks is we're finding this whole area here. Let's just color it in a little bit so you can see it. Okay, so this is an even function. And so just visually, you can tell why this fact is true. The area under the curve and above your x-axis from negative a to a is just twice the area if you look at half of it. So if I cover up half, actually let's cover up this half. If I cover up half, find that area from 0 to a, and just double it, I get the whole area because it's symmetric. Okay, so that's one way that you can use the symmetry if you know that your function's even. And so, real quick, you can tell your function's even if this is true, if you plug in negative x and you get out the same as if you plugged in positive x. Or the other way to tell is from graphing it, if it's symmetric about the y-axis. Okay, that's one of two possibilities. The other one is if the function is odd. So if your function is odd, which you can tell if that's true, if you plug in negative x, and it's the same as if you were to just put a negative on the outside of your function, you get the same result, then the following is true. Your integral from negative a to a of f of x dx is 0. That was kind of interesting. Let's draw an odd function so you can see it. So two ways to tell that your function's odd. One, plug in a negative x, see what you get. Put a negative on the outside of your function, distribute it, and they should equal. Okay. The other way is looking at the graph, and in this case, the graph is symmetric about the origin. So if I draw a quick sketch of an odd function, it might look something like this. So it could do maybe like this. Okay, this is an odd function. And so if I'm finding the area between the curve and the x-axis, this is what I'd be calculating. This area here between the curve and the x-axis, this area here between the curve and x-axis, this area here, and this area here. So if I know my value is going to actually represent area and I'm told find the area, I would want to take the absolute value of my integral because area should be a positive number. But if I'm just calculating the integral, so kind of distinguish these two ideas. If you don't specifically have something that says find the area, then if it just says calculate the integral, it's okay for it to be negative. So what I'm trying to point out to you is that this area would be positive, this value, but this one will be negative. This one will be positive, and this will be negative. And so they would all add up and cancel out and equal 0. So if it doesn't actually say the word find the area, then you keep it the way it is, positive and negative, and the result would be 0. If it says area, then you have to just take the opposite values. And we'll do some area questions next, area between curves. So just some facts for you real quick again on this one. A function's odd if this is true, or if there's symmetry about the origin. Okay, just notice if I put like a little pivot point here, my function is symmetric about the origin. It's even if it's symmetric about the y-axis. Okay, so now we're ready for the area between curves. Okay, so area between curves. All right, let me give you some like fine print statement, just the background, and then we'll get into our integral. So if f and g are continuous, and this is with f of x, so f or f of x is always going to be greater than or equal to g of x. Okay, there's a reason why one of them has to be bigger, and I'll explain and show you why. So if f of x is always bigger or equal to g of x, and this is throughout some interval from a to b, so throughout a to b, let's make that look a little better, that's a bracket, then the area of the region, so the area of the region between the curves y equals f of x and y equals g of x, and this is from a to b. Okay, we don't need this anymore. From a to b is the integral of f minus g from a to b, which looks like the following. So area equals the integral from a to b of the integrand is f of x minus g of x dx. Okay, so if you have two curves and you want to know about the space between them, specifically the area between them, one of them needs to be the top function or upper boundary function. The other one has to be lower. That's this part right here where I said that f of x is always bigger than or equal to g of x. So then we say that we take the upper boundary or upper curve, we'll call it upper boundary. Upper boundary, and it's boundary of the region that we're integrating. So the upper boundary, and we subtract the lower boundary. And then what that gives us is the space between the two curves. So just a quick image for you so you can understand this part. If you had, let's say, let's just draw this real quick. We'll say from maybe the top curve does something like this. Okay. So if I want everything below this top curve, is what I was calling f of x, because I'm claiming that's always bigger. But then I want everything above the bottom curve. So we'll say it's like this. This is g of x. The way that I get what's in between them is the subtraction. It's the leftover part. So if we kind of color some stuff in real quick, if I said everything below f of x, it would be all of this blue. It would technically go down forever. And then if I wanted everything above g of x, that would technically go all the way up to infinity. But I want what's in between them, and so by doing subtraction, I get this in between part, this subtraction piece, this difference. And that's what we're doing with the subtraction. That's why in the integrand, we're subtracting. And one of our functions is always considered the top, one is always considered the bottom, and then when we subtract, we get what's in between. So that's how we find the area between the curves. So let's jump right into it and try out an example. So I'm going to start it up here. Let's say we want to find the area of the region enclosed by the parabola, which is going to be y equals 2 minus x squared, and the line y equals negative x. Okay, I'm going to draw this one for you so you can visually understand what's happening. You don't always have to draw problems like this, but a lot of times I think it will help you guys set it up. Okay, so one thing to notice is I actually didn't give you any limits of integration, so all of that has to get found out during our work. We also don't know which is the top function and which is the bottom function, so that's why in this case drawing it's going to help us. But sometimes you can just sort of play around with some values and see which one's going to be the upper function or upper boundary. So I'm going to start with my drawing of my region. We know we are trying to find the area enclosed by two curves. Technically this one's a straight line, but we still consider that a curve. So this curve and that curve. So this is a downward parabola because it has a minus x squared. And so that's going to start at 0, 2. And let's see, I'll go ahead and draw that one in blue. So 0, 2, go. And then for a parabola, that's going to go down 1 and over 1. And then we can go over 2 and down 4. And just remembering what I knew when I learned about graphing parabolas, we go over 1 and technically it would have been up 1, but this is downward, and then over 2 and down 4. Okay, so let's draw that really quick. Just doing a quick rough sketch of this parabola. Oops, put a miss back there. Okay. Let's draw straighter, sorry. Let's get that in there a little better. And this one here. Okay. So that's my parabola, y equals 2 minus x squared. And notice I stopped drawing it. I could keep drawing further down, but let's see what's going on with the other boundary, and then we'll see how much more, if any, that we have to draw. Okay, so my other one is a line, and 0 will give me a 0. So this is a line through the origin with a slope of -1. So I'll just go down 1 over 1, down 1 over 1. I can even go up 1 and left 1. Okay. And so this is our line, y equals -x. So what we're finding is this region's area right here, enclosed by the curves. So I want to know about this space. What's the area of this shape, this region? That's what we're finding. So by our drawing, we identified the upper boundary. What's always the higher y value, if you want to think of it like that, the higher y value is always the parabola. So this one is the upper boundary. And the line is always the lower boundary. It's the lower y value for our entire red region. So this is the lower boundary. And now what's left to find is the limits of integration. So I actually need to find right here what this x number is and what this x number is. Based on my drawing, I can tell what they are, but let's say my drawing's not that accurate, or I didn't even draw it in the first place. We're going to find it by figuring out where they meet. So I'll say to find the limits of integration, we'll say set functions equal to each other. And if you think about it, that's because when they're equal, they meet. Okay, so set functions equal to each other. When they're equal, they meet. Those are the meeting points. So if I say y equals 2 minus x squared equals y equals negative x, okay, these both equal y. So set them equal to each other, or use substitution. Let me make this more clear. Substitution. Substitution. This is what I'm trying to make clear really quick. They both equaled y. That's why I can set them equal to each other. Let's say one of them was not in the form where it equaled y. You would substitute the other one into that function. It's from algebra. When you had two equations and you wanted to solve, you could use a substitution method, or elimination would work as well. So if I solve this, let's see, I have quadratic. I'm going to go ahead and bring everything right. So I have 0 equals x squared minus x minus 2. It is a quadratic equation, so we either need to use a quadratic formula or factor. This one's going to factor pretty well, so let's just factor this out. So I need 2 and 1, and I need to multiply to get a negative 2, but add to get a negative 1. So this is x minus 2, x plus 1. So that lets me know if I solve, each one of these equals 0, x is 2, and x is negative 1. Okay, so my x value here, and again, I could tell from my drawing, but let's say I couldn't. X went from negative 1 to 2. And so those are my limits of integration. So now I'm ready to do my whole setup to find the area between these curves, this red region. So the area here is going to go from x is negative 1 to 2, and then my integrand, I subtract my upper boundary function minus my lower boundary function. So I'm going to say 2, let's do it in colors so it lines up. I'm going to say 2 minus x squared as my upper boundary minus my lower boundary, which was negative x. And this is all in terms of x, so dx. And now that I have my setup, at this moment, this is not new. We know how to solve this integral. The setup was the new part, how to figure out how to set this up. So now let's quickly just go through it. If I simplify my integrand, this is going to be negative x squared plus x plus 2. And if we use our power rule, this is negative x cubed over 3 plus x squared over 2 plus 2x evaluated from negative 1 to 2. Okay, just use my power rule to integrate each term. And now I'm going to plug in my limits of integration and then simplify. So I have negative quantity 2 cubed over 3 plus 2 squared over 2 plus 2 times 2. And then for my fundamental theorem of calculus, minus what I get when I plug in negative 1. So negative 1 cubed over 3 plus negative 1 squared over 2 plus 2 times negative 1. Okay, so the rest is just a quick computation. I won't make us go through that, but you will get 9 halves. So we have 9 halves, or 4.5. And because this is area, we're going to go ahead and say square units. Whatever our units are, they're squared because it's area. Okay, so that's our first one for how to find the area between two curves. you have to identify an upper boundary and a lower boundary, and then if the limits of integration aren't given, you have to calculate those as well. What I want you to notice is one way to kind of approach this region is to think of taking a slice out of it. I didn't draw this earlier, but let me just draw it now. If I could take a chunk out of this region, that's how I can come up with what's the upper boundary and the lower boundary. Let's just color that in a little bit. So no matter where I decide to take this slice, the upper part of my slice will always hit the blue parabola, and the lower part will always hit the green line. And so that's how you can figure out the upper and lower boundaries. And why I'm mentioning that is because it's not always going to be the same upper and lower boundary. And I'm going to show you what I'm talking about right here with our next example, so you understand the difference. So let's see. I think we can. I just drew that slice, but I'm going to go ahead and start erasing. So I'll leave that there for a moment and just right up here. So let's see. We're going to find the area of the region, and this is going to be in the first quadrant. So first quadrant, and it's going to be bounded above, and it's bounded above by y equals square root x, and below by the x-axis, below by the x-axis, but also the line, so I'll say and the line y equals x minus 2. Okay, so I'm going to draw this one also so that you can get a good visual for it. So we'll do this same kind of thing where we consider taking a slice out of our region. So this one, we have the area of the region. It's in the first quadrant, meaning if you separate your coordinate system into 4, remember how this goes from trig? Let me just start drawing it here. Your coordinate system, we go 1, 2, 3, 4, counterclockwise. So this is quadrant 1, where everything's positive. So first quadrant, above by the square root of x. So let's draw that one. So square root of x, if you plug in 0, that's your first point. If I plug in 1, I get out 1. Let's draw this in black. 1, 1. Actually, let me space this out a little bigger so you can see it. Let's go here with 1. 1, 1. And next would be 4 to give me 2. If I plug in the square root, 1, 2, 3, 4. Okay. All right, there's our square root function. I just plotted a couple points. Y equals square root x. Next, let's draw our other boundaries. We have a lower boundary as the x-axis. So our x-axis is a lower boundary, which is x-axis is y equals 0. So it's this whole thing here. But also the line y equals x minus 2. So let's draw that line. So I have a y-intercept of 0, negative 2. Okay. And then my slope is 1, so I'm going to go up 1 over 1. Let's go up 1 over 1, up 1 over 1, up 1 over 1. Okay. Just a quick hand sketch of our region. This is y equals x minus 2. All right. So let's like fill in the actual region that we're integrating so that you can see like the enclosed part of all this where they all overlap. So the region in the first quadrant, so it has to be in the first quadrant only, bounded above by the square root, below by the x-axis, and below by the line. So it's this region right here. Below by the x-axis, below by the line, and above by the square root. So this is our region that we're integrating. So you kind of had to just piece all that together with the words that it was in the first quadrant as well. So there's a lot going on here. If I start to draw a slice in my region, look what happens. If I draw a slice here, if I take out a slice here, let's identify some stuff. The upper boundary is our square root function, okay? So it's y equals square root x. Okay, and then the lower boundary right here, the lower boundary, let's just draw it here. Lower boundary is the x-axis, which is y equals 0. Okay. Let me draw another slice. Let me take another chunk out of this region. How about I draw it here? I take a slice out of my region right here. Okay, my upper boundary is still the same. It's still the square root x, but my lower boundary has changed. So the lower boundary, let's go ahead and erase some stuff. It's getting crowded over here. Okay. Don't need any of that. So our lower boundary here is, let's erase that. Y equals x minus 2. I'm going to erase this as well. That was just labeling our line. So this one's a little different because we have two lower boundaries depending on where we look, where we take a slice of our region at in order to integrate it. So what we have to do in this case is we have to separate this into two regions. So I'll say notice we have two lower boundaries. So what this implies is that we have to split the region into two regions. Okay, and so we split it where it changes. So I'm going to split it right here, right at the switch, right where the line and the x-axis meet, we have to split. Okay, so let's draw that really quick. If we kind of just redo the drawing briefly, I'll do it in red, just so you can see it more clear. We have something like this, and like that, and like that. Okay. So we have region, I'll call it 1, and region 2. So region 1 and region 2. And then we just integrate each region and add them up to get the area. And so let's label some boundaries. For region 1, look at where we're at. We go from the starting point on the x-axis for our region, which is 0. So x goes from 0, and then we stop that region right here, where the line and the x-axis met. So if we couldn't tell from our drawing, we could do a quick computation. We would say that it's where y equals 0 meets y equals x minus 2. So we can get pretty quickly that x is 2. So from 0 to 2, we're in the first region. Then the lower boundary, let's put on some boundaries for y. The lower boundary for y in this first region is the x-axis. Okay, it's the x-axis. So the lower boundary was y equals 0. In that first region, the upper boundary was still the square root. So square root x. All right. Now, on region 2, let's go with x. X starts here. We just figured out that was 2, and it goes all the way to here. If we hadn't seen this from our graph, we can do a quick calculation. The square root meets the line, and you can say, okay, the square root y equals square root x meets the line x minus 2, and then you can solve for that pretty quick. We'll do it really fast. So if we square both sides, we get x equals x minus 2 squared, and then we get x equals x squared, excuse me, minus 4x plus 4. And so 0 equals x squared minus, it's going to be minus 5x plus 4. And then we can factor this one, and we get x, this is going to be 4 and 1, minus and minus. X is 4, x is 1. Is that right? X is 1, did I meet? Get my math right. I know they needed x is 4. Why did I get a 1 here? Negative, that adds up. And they don't look like they needed x is 1. Where is my drawing? Okay, talking to myself for a second. Sorry. Pretty much, we were just solving for this number here. We can already tell from looking that it was x is 4. So we say that x goes from 2 until 4 for our second region right there. So from 2 until 4. And then our y values, our lower bound in this region, the lower bound, the lower y value was the line x minus 2. And then the upper bound was still the square root. Okay, so we're going to add up the two integrals to figure this out, this area out. So let's go ahead and let's go up here. Okay, so we have our area equals one integral for region 1. X goes from 0 to 2. And then our integrand is our upper boundary minus our lower boundary, dx. And then we have to add the second integral for our second region. So we have this region that we just wrote the integral for the area. And now our second area is from x is 2 to 4. Our upper boundary was square root x. And then minus our lower boundary, which was the line x minus 2 dx. Okay, so the main idea on this one was to show you the setup, and then we would integrate this accordingly, and we would just add up the two answers to get the total area. So it was a little bit of a process, but what I want you to recognize is if you ever have, depending on where you can take a slice of your region at, if you have two different boundaries, whether it's top or bottom, upper or lower, then you have to split your region into two parts. If it's three different boundaries for top or bottom, then you have to split it into three parts. So depending on how many possible combinations, I'll show you another one so you see what I'm talking about, like with 3. You don't have to draw this, just sort of look at it real quick. So let's say my region looks something like this. Just make this up real fast. Let's say I had a curve and it went like that, and I wanted to know where it met with, let's say, this curve. Should have did colors. It's getting a little messy. And I wanted to match it with this curve as well. This is ugly, but let's say we were integrating this region, and then this region, and then this region. Okay, sorry, I know it's a little hard to see, but the point is to show you, you would have to split this into 3 integrals, because here, your lower bound would be the line. The upper bound, you'd actually have, based on my drawing, you'd have to split this up as, again, because I have 2 upper bounds. It's not a very good drawing, but here you'd have your lower bound is the curve, the upper bound is the line. Down here, lower bound is the line, upper bound would be a curve. So sometimes it's more than 2, but often it's two regions. Okay, so that's the setup. But what I want to do with you, instead of calculating this, you can calculate this to verify. I'm going to show you that you have another option here. So all of this is one way to do it, but if you find that you have to split your region into two parts, you can try doing it differently. You can try doing it with respect to y instead and see if it makes it easier. And so in this case, we're actually going to do that. So just so you know, if you do the work here, you're going to get 10/3. Okay, so if you want to check that just to verify, you can see what you get. But we're going to do it a different way. We're going to integrate the same region, but with respect to y this time. So I'm going to erase all this because it's gone a little messy, but I'm going to redraw it just briefly. Okay, so let's talk about this real quick. We are going to integrate with respect to y. So with respect to, okay, with respect to y, the area is the integral, we'll say from c to d, and this is going to be f of y minus g of y dy. Okay, so here, these limits are y values. Y is between c and d. And then your functions are going to be rewritten in terms of y. So if you're doing this in terms of x and y, you don't actually want to call it an upper boundary anymore. You actually want to call it a right boundary. So this is the right boundary. And instead of calling this the lower boundary, you actually call it the left boundary. Okay, so we're going to do the same exact problem, but in terms of y this time. So you can see that it's actually a little bit of an easier setup. So let me redraw what we had, just a quick redrawing of it. So let's see. We had 1, 2, 3, 4, and I think we went up to 2 here. Okay, so the top looked like our curved square root. The bottom had the straight y equals 0 right here. And then at 2, we had our slanted line. Okay, x minus 2. All right, so just a quick redrawing of our region. That's our same region. It just, I kind of smashed it down so it's smaller. But now, if we take a slice, we're going to actually take a slice horizontally, and then you can see that there's only one right boundary and one left boundary if we do it this way, instead of upper and lower. So if I take a slice out of my region, no matter where I decide to take that slice, down here, all the way up here, no matter where I slice horizontally, the left boundary, so the left boundary is always going to be that square root curve. So the y equals square root x. And no matter where I take my slice, the right boundary is always going to be that line, y equaled x minus 2. Now the issue is, because I'm doing things horizontally now, a function of y, I have to change everything to be x equals something in terms of y. So I need to adjust my equations for my curves. So what I have to do here is I have to rewrite. So I'm going to rewrite, and I'll say in terms of y. Okay, that might be hard to see. It says rewrite in terms of y. So y equals square root x. If I just do some solving really fast, if I square both sides, I'm going to get that this is x equals y squared. Okay. Then for the other one, y equals x minus 2. If I add 2 to both sides, I'm going to get x equals y plus 2. So these are my new functions. They're the same functions, but they're written in terms of y, so that I can plug them into my integral here with y as my variable. So now our area here is going to be from my lowest y value to my highest y value. And so for us, earlier, this was the point we figured out where the line met with x squared, or square root x. And if you plug that in and solve, let's see, that was when, that was 2. This was 2 on the y-axis. Okay, so y, I'll just put it very clearly, y goes from 0 to 2. And so my right boundary, my rightmost boundary, was the line x minus 2, but when we just solved in terms of y, it looks like y plus 2. And then minus my left boundary, which was square root x, but when we solved in terms of y, it looks like y squared. And then dx, or dy, sorry, dy. Okay, and then I just want you to notice, this is so much easier because we don't have to do 2 integrals, let alone work with square roots. So let's just do a little bit of integration really quick on this so that you can see that we're going to get 10/3. So this is going to be y squared over 2 plus 2y minus y cubed over 3, evaluated from 0 to 2. And if I plug in 2, we'll just do it real quick by talking. 2 squared is 4, so 4 over 2. And then 2 times 2 is 4. And then 2 cubed is 8, so 8 over 3. And then if we plug in 0, this is going to be 0 plus 0 minus 0. And that would give us 10/3 if you find a common denominator. Okay, so let me make sure that you understand this process. Sometimes it's better to change the variable that you're writing all your things in terms of, your function, your limits, all that, if it will stop you from having to use 2 integrals instead of 1. You can use 2 integrals, it's perfectly fine, but sometimes it's easier to just change your perspective for how you approach the region, and then this integration was a lot nicer than this would have been. Even the setup was longer because it was 2 integrals. So what we did over here, so you basically think about bigger numbers. So in the first instance, when we were integrating with respect to x, the bigger numbers were higher up. Okay, upper bound was bigger numbers minus lower bound, which is smaller numbers. In terms of y, the bigger numbers are to the right because x is bigger over here. So when x equals something, the bigger numbers are to the right, and then the lower numbers are to the left. So it's always bigger minus smaller, in this case, right minus left. In terms of x, bigger minus smaller, upper minus lower. So if that helps you remember which subtraction to do, it's either right boundary minus left boundary or upper boundary minus lower boundary. Okay, so I think that's it for this one. Hopefully you guys feel okay with this, at least be able to approach this process and just spend some time on it. And then if it's, just remember when you do switch to your other variable, that you need to rewrite your functions in terms of that variable. So you just usually have to do this quick solving on the side. And then don't forget that your limits have to be in terms of that new variable as well. Okay, everybody, have a good day.